Thank you. Thank you, Dr. Adhikari. And hi, everybody. So we just heard from Dr. Sadona on his powerful optical imaging technology. So in the next 20 minutes, I'm going to switch gear to share with you about optical manipulation. So the work I shared mostly is done, it's a collaboration between my group and a lot of collaborators. And when we think about optical manipulation, optical tweezers has become one dominating tools, which enable us to advance many fields, in particular in biology. Simply speaking, the optical tweezers are based on optical scattering and gradient forces, which provide us a tremendous advantage in studying biology because it's can be remotely controlled using light. And it's versatile manipulation, which means you can using computer actually control the laser beam to achieve arbitrary control in 3 dimensions. Also, the objects that can be manipulated in terms of size is fitting well with a lot of biology organisms components at the nano micrometer scales. But they do have a few limitations that prevent a more broad use of these powerful tools for other applications. First of all, it's a high power because typically the optical force window is quite weak, right? So we need using a high power laser beam also often be highly focused to generate this gradient force. Also, because of the nature of this force, it requires that the particle we are going to trap or manipulate have a good contrast in terms of optical properties with the surrounding media. Typically, is a solvent for biological study. And so because of high power, it can cause damage. In particular, if you go to smaller particle in nanoscale, molecular scale, your power even higher. So that's can potentially cause damage. And also, many application or many demonstration has been limited translational motion, even though there's a lot of beautiful work on rotation too, but typically require very complicated engineering of the laser beam to achieve rotation. So this limitation motivated us to think about a new approach to hopefully overcome some of those to broaden the application. So the approach we take is take advantage of the heating effects, optical heating, which is a theme of this webinar. We see a lot of great work on how to harness optical heating for the thermal effects in imaging, in manipulation. And in this talk, I'm going to share 3 scenarios which we have pursued to enhance the optical manipulation capability. So with the goal of the reason we harness optical heating, we have a few goals. The first is that we hopefully, by using optical heating effects rather than optical forces, in an indirect way, we can use lower power to achieve the similar manipulations. And also, we may overcome the difficulty to set up a very sophisticated setup rather than using a very simple system, maybe even laser pointer to achieve a manipulation. And along with this low power simple optics, we also demonstrate that by using heating effects, actually we are able to expand the current manipulation mode of optical tweezers. And also we can make this manipulation beyond typical liquid environment into solid environments. So the first scenario is the mechanism, what we take advantage is called thermophoresis. So we're using laser beam instead of using optical force. We're using laser beam to heat substrate to create a temperature gradient. And through this temperature gradient, we introduce thermophoresis, which typically particles in solution will move from one side of the temperature gradient to the other side. But the difficulty in using thermophoresis is that in many cases, actually the particle is moved from hot to cold region, which become problem because we hope that the particle can follow our laser beam, but unfortunately, laser beam heat up the environment, push the particle away. So this is vividly demonstrated by Dr. Frank Citos, he shows that if you put the plasmonic particles, which have a really good heating effects, and actually you can push the particle into colder region. But interestingly, you can arrange these particles in a ring configuration so that in the center is colder, right? So that you can confine the particle in the center. But then we think about in this still, it's a beautiful demonstration of used thermophoresis, but in terms of manipulation, still limited in terms of dynamic control, right? You can only confine particle in the one position, but you cannot versatilely manipulation in 3D in space. So we take a different approach, try to overcome this kind of particle prefer to colder region. Instead, when we add a certain type of surfactant in the solution, we can create a very interesting phenomenon we call the thermoelectric field. If you look at this cross-section, we have this substrate which can absorb laser beam, generate the heating, and create a temperature gradient. So in this solution, there's a particle we're interested to trap, but we also add a surfactant. So the surfactant serves several roles. One is coating the particle to make it become charged. In this case, a positive charge. Also, when you add enough, they form micelle. So the micelle is also positive charge, but smaller in size. Also, in the surfactant, you have negative ions. So we know under this temperature gradient, all the particles will move away from the hot region, the laser spots, towards the colder region. But interesting phenomenon happen is that the movement is very different between the micelle and the ion. So micelle is faster, ion is slower. So there's the separation. Now you've created this electric field, positive, negative, and the particle have a charge. So you have this electric force that trap the particle there. So by doing this, we introduce what we call optothermoelectric tweezers. So using this tweezer, we can overcome a few challenges for conventional optical tweezer. Not only we can reduce the power in about 1,000 times, but also we can capture even metal nanoparticles, which have plasmonic heating effect very strong. Typical optical tweezer, if you trap it at the resonant wavelengths, it's really hot because of a very strong Brownian motion. But in this case, since we're using indirect way, we're using thermophoresis, and we can do this metal nanoparticle even at the resonant wavelengths. And another interesting thing using this system is that we can introduce the bonding between the particles. In conventional optical tweezer, you hold the particle in some position using laser beam. When you turn off a laser beam, it go Brownian motion, run them again. But here, we actually can hold it to particle close enough that introduce what we call attractive depression force to bond the particle together. So basically, we introduce an artificial bond between two particles. We form artificial matter. But more interesting thing that this bonding is dependent on the concentration of the surfactant that we add in. So when you add less, the bonding becomes weaker, the bonding length is longer. If you add more, the bonding becomes stronger, the distance between particles becomes smaller. So in plasmonic, we are familiar that this distance can affect the coupling between two particles, introduce very different plasmonic modes. So basically, this approach provided us the capability to create tunable artificial matter. So we can, just like we play Lego piece, right? We can hold these pieces using hand and put them together through the logging effect. But here, in an analogy to this Lego piece, with the colloidal particle at the micro nano scale, we can using optothermoelectric tweezer to hold them, but meanwhile, this depression attractive force to bond them together. So we can build any type of superstructure using these colloidal particle as a building block to create what called the metal materials or metal molecules, one by one, or in plural. So this video shows that we can do this in plural, and simultaneously, we can hold multiple particles, or we can do one by one. Right? So different from optical tweezer in this case, when your laser beam move away from the cluster we already formed, actually they stay there because this kind of bonding maintain this superstructure. And we can do this for all sorts of particles. As I mentioned, we are not limited by the type of a particle, the composition, size, shape. So we can create all sorts of superstructure, which optically become interesting because this kind of interparticle interaction can lead to new optical properties. And further, since we can reduce the power now, so one laser beam, we can use a DMD system or special SLM, special light modulator, to split one beam into many, many beams. Since the power is low, so we can create much more beams than conventional optical tweezer. And this enables us to manipulate particle in a larger quantity. So one of the goals for us to using this advantage of many, many particles can control individually, provided what we call it wisdom, so they can have their own control of direction, the sense of the environment. And we can study a very interesting phenomenon called collective motion. And collective motion, which is very common in nature, from different side, a different type of living species like ants, birds, a school of fish, or even with human being, the social interaction, somehow we form this kind of collective motion or follow certain rules. And we can show that in some of fish or bird actually are very simple rules. The rule is that the neighboring particle or neighboring boats will align their velocity, can achieve collective motion. And so in the lab, we can use this micro nanoparticle as a bird, and using our laser system, actually we can show that this principal algorithm actually can reflect what happened in nature. So this gives us a powerful platform to tune the parameters, to compare with actual observed in nature, to understanding more sophisticated mechanism dominated different type of collective motion. Or we can use this type of algorithm into autonomous cars, robots, to facilitate a better efficient communication, a better transportation or collaboration between different robots. And furthermore, we can even expand the manipulation mode. As I mentioned, conventional optical tweezer limit to translation or some rotation in the very unique conditions, but using optical effects, we can simply control the distance between the laser beam and the particle we're interested. We can create more manipulation mode, like rotating or rolling, like in bowling game, or shooting, even printing down on the substrate. So when you create these different modes, expanded application opportunity. So as a demonstration for this rotation capability, we show that by simply rotate algorithm, organism, or bacteria or virus, and we can use a standard simple optical microscope. Of course, super resolution microscope is very powerful, including what Dr. Doda introduced, the scattering interference imaging, very powerful to reveal very details at the micro nano scale. But using standard microscope, we can kind of circumvent the limitation in 3D imaging by rotation. So we can rotate it and image at the same focus plane, but we can reconstruct the back, so we can get 3D images. And we can further combine with machine learning, which become a really powerful tool to image analysis. And that, but the limit for machine learning is that the training. We need a lot of data to train the algorithm. So in our case, if you want to using this machine learning to identify different bacteria, the different strains of the same type of bacteria, and you need a lot of data to train a lot of optic image of these bacteria. But which means you need a lot of samples. But we can circumvent this limit by using much less number of bacteria, but rotate them. For each bacteria, we can rotate them at a different orientation, take an image. This can create many more data as a training. So you can see, even though we're using 24 cells compared with 240, we can still get an even good accuracy when we're using those to training machine learning. So less training, more time efficient, but still get a good accuracy in tell the difference between different strains of bacteria by combining rotating, 3D imaging, and the machine learning. And since it's rotating, we can develop this into rotational adhesion frequency assay, which is very important for biology because cell-cell interaction adhesion is at the core of many, many biological functions. So we can monitor this rotation behavior of this cell when they interact with the substrate or other cells. So we can kind of, through static analysis, we're able to derive the adhesion efficiency of the cells, simply monitoring this rotation behavior. But you may question, Since we use a heat effect, in some cases, biology maybe don't like get heat up. It may kill the cells. So we further develop the technique called hyperthermal, which means we can reduce the environmental temperature, so we can keep a safe environment. But another advantage by cooling down the environment is that in some cases we can flip the motion direction from hot to cold region, or from cold to hot region. So we don't need a surfactant anymore in this case. Simply cool down the environment, we're able to trap in the biological cells in a much simpler solvent, even in their own biological solutions. Another case maybe become more straightforward is that why not just cooling the substrate using laser? So using laser beam to cooling atoms has been a very dominating research field, which also awarded with Nobel Prize to cooling the atoms and molecules. But recently, researchers started to discover that actually laser can also cool solid materials like semiconductor materials. So by introduce this very unique substrate that we introduce here, and using laser beam to cooling the substrate, that we introduce temperature gradient. But in this case, the laser position is colder. So it's very natural for many thermophoresis happen from hot to cold, and we can trap the particle at the cold region. Meanwhile, we can keep them safe because there's not much heat effects. Actually, it's a cooling. Now I move to the second scenario, which using purposely increase laser power a little bit more, so that in this case, we introduce a bubble. 2 weeks ago, the Dr. Nikkei Shell from Sweden and his students introduced this bubble phenomena, and they're really great work about how you can control bubble temperature gradient to control the convection flow through the Mangaloni effects. And we're using these bubble effects to create what we call bubble paint lithography technique, or what we call bubble printing. And just a quick video show that.
Drive it to the back of the moving truck.
Yeah.
This is basically that.
Exactly.
What's old is new again. To Texas now. Where's that? Scientists have mastered another difficult maneuver. It's no Knight Rider, but it's pretty good. How do you manipulate microscopic nanoparticles? Well, it's simple. You just trap them in a micro bubble and then use a laser to move them around. That's what engineers at the University of Texas are doing. They call their technique bubble pen lithography. Moving the nanoparticles around with bubbles avoids handling them directly, and that lowers the risk of damaging them. And these are great tools when scientists want to start building their tiny futuristic machines.
So the convection flow can collect whatever in the solution, right? So we can print different particles, even a few nanometer Conan dots. We can form a cluster, depends on the size of the bubble. Now we can continuously printing. And we can even collect the ions, and these ions as a precursor, and they can be confined at this micro scale nano region, which give you what called micro reactor to create even chemical reaction which conventionally cannot occur. So we can form a very interesting nano alloys, work as very powerful catalysis, or create a metal nano structure for plasmonic applications. And even we can collect a molecule, which we take advantage of this capability for sensing. Now, in a lot of sensing, in particular nanosensors, it's very sensitive. But the limitation is that in the case that we have a large volume of samples, which have very, very low concentration of a biomarker we are interested, the diffusion will take a lot of time for them to reach the surface of the nanosensor, which only there they can detect, become high sensitive. Otherwise, it won't work since it's the nano scale. But we can use a bubble and take advantage the intrinsic property of a plasmonic effect as a sensing signal, but also the plasmonic effects heating to create a bubble using low power laser to collect the molecule at the surface of these metal materials so we can detect the molecule. One example, we can use this to detect the biomarkers, in particular the chirality of the molecules, biomarkers in the urine, to monitor the diabetes. And typically we're using glucose in the blood. But here actually we show that the total chirality change of those metabolites in urine, and it can also be a powerful indicator to show the diabetes, and the sensitivity is not worse than glucose detection. And we can use even using this bubble printing to coat a particle on any surface. And of course, in many cases, we need using the surface can absorb light, generate heating. But in order to make it more general, we can use a femtosecond laser, which can make many surfaces become absorption of the light, become heated up. So we can, in this case, we can use a femtosecond laser generate bubble printing to create those magnetic particles on the insect. So we can use a magnetic to control the behavior of these insects. So we are trying to use this behavior to actually to interfere the insects or the fish or birds, hopefully to try to understand the collective motion in a more deep level. The last scenario, the third one, before I conclude this talk, is based on these thermal effects, we can also break the boundary of many optical manipulation based on optical force is in the solution or in the vacuum environment. Actually, now we can move in the solid surface, substrate. And the working principle is that if you have this golden nanoparticle on the substrate like glass, we can coat in a thin film of CTSC, the same type of surfactant we use in the thermoelectric tweezer. In this case, that serves a different role. So in the beginning, there's a strong adhesion between particle and this CTSC layer, but if we heat the laser beam on this particle, it gets heated up. So the heating will melt this layer of CTSC layer a little bit, become quasi liquid. So the adhesion between substrate of the particle become weaker. So we can use a scattering force from a laser beam to push the particle. That's how can we move. We call nudging, optothermal guided photon nudging. So you can see we can put a one silicon nanowire, we can move this silicon nanoparticle towards this nanowire, and we can control their position. Optically, we show that because of the position of this particle, we're able to generate a chiral structure. If asymmetric with a chiral, if at the one ending, it's become chiral structure, so chiral responses. And even we can control the laser beam position and the particle size shape, we can create rotating, and we can call the motor effects. So you can see this can, using laser beam, simply point to the position, and the particle will orbiting, circulating around the laser beam continuously. And this phenomenon can be modeled and based on the thermal Capri effects. We can even move into three-dimensional manipulation. Even though the particle is embedded in the polymer matrix, the similar thermal effects, we can able to manipulate this particle in 3D. So we can create what we call photonic crystal or superstructure in the solid phase. So whenever we turn off the laser beam, it will stay there very stable. So we can study their interesting optical properties. So as a summary, hopefully through the three scenarios or three directions, hopefully I kind of give you some sense. How can we harness the optical heating effects? In many cases, actually, we assume is a negative effect or optical loss, but can be our advantage to create a new type of manipulation capability. And this heat-mediated optical manipulation is very rich in physics because we can explore all sorts of working principles, not only thermophoresis, what I had, or thermal electricity that I have demonstrated, or in the bubble of the thermal flow, we can also explore other phenomena like photothermophoresis, or even optothermal deformation effects, or diffuser phoresis. By combining different media, different type of light source, or different type of objects we are going to manipulate. You can explore all sorts of working manipulation mode, and not only translation or rotation, or even walking, oscillating, trapping. This manipulation mode become a very basic mode for robotics, a micro nano robotics, or they can work to enhance optical sensing or biological analysis by combining very powerful optical imaging, optical spectroscopy with this manipulation capability. Or we can use this to create new materials by assemble colloidal particle, covalent dots as a building block, or using this as a functional components in optics or electronics, or using as a platform to understand fundamentals of the material science or optics. Or we can use them to create a new type of micro nano robot for drug delivery discovery of fundamental biology. Yeah. So hopefully this can inspire interest to start looking into this field, to join together to push this field. So thank you for your attention, and thank you our organizers for this fantastic platform to provide for the community to engage this emerging field. I'm happy to answer any questions.
Yeah, thank you very much. It was a wonderful talk, a lot of nice works. This is now open for questions, and we have already one questions in the chat. Question from Godoy is, how do you push the particles at different G position at the very last slides?
Very last slide here.
Yes,
Yeah,
I think.
so in this case, we're using called a thermal capillary force. So it depends on the laser focus point position, we're able to push along X, Y, Z directions.
Okay, you can write your question chat, or you can directly also ask. So I have a quick question regarding the chirality, where you use the bubbles to detect left-handed and right-handed. And so how does the detection really, how do you recognize the left-handed and right-handed molecules?
Exactly. So the function of the bubble is the purpose is to collect the molecule to the surface of this substrate. So this substrate is unique. That's why it can distinguish the left hand is right hand is because it's a chiral. So this substrate is actually it's a two layer of nanohole array of gold. And we stacking them together, we twist it. So form this what we move pattern. So when we twist it, we introduce chiral effect. So actually, this is a chiral. So when we did, measure the CD signal of this layer, actually there's a very strong CD peak. So, but interesting thing about this CD peak is that it's very sensitive to the molecule attached to the substrate. If the molecule is left-handed, it will cause shift different from right-handed molecule. So by analyze this shift difference, we're able to tell the molecule is which handedness.
Yeah, that's nice. Are there further questions? Okay, I think we will, there is a question from Professor Kobayashi. How is the limit of size to manipulate?
How is the limit of size to manipulate? For in terms of bubble, it's a times it's we're sure it's even can do in ion molecule. For the some electrical tweezers, it's the limit is by the imaging capability, and we can manipulate down to a few nanometer, even much smaller. In theory, there's no limit, but for demonstration, we always limited by the imaging capability. And if you want to image a few nanometer, it's hard for us, in particular in this kind of dynamic situation.
And he asked also about the larger size, means how large size particles you can manipulate.
Yes, larger size is for bubble. It's can be much larger, and you can go to a several hundred micron as long as it don't stick to the substrate. And for some electric tweezers, typically we work reach to maybe 20, 30 micron. It depends on materials also.
Okay. Is there further questions? I think we'll open for this. Oh, I think there is a question from Julian. Thank you for the talk. There is a slide at the beginning of the talk where you show a controllable coupling between two nanoparticles. Can you please provide more details?
So here, so yeah, in this case, we bring two nanoparticles together. When they're close enough, the micelle will not be fit into the gap between two particles. So now you have imbalanced concentration of micelles. You have more micelle surrounding these two particle pair, which simple explanation, those micelle can provide maybe Brownian motion. You can push these two particles together. So they will stay there. And we know plasmonic, when they have close enough, the near field coupling can induce longitudinal mode. For otherwise spherical particle, only one dipole mode. So longitudinal mode, transverse mode, you can introduce two peaks. And this two peak depends on the distance. So the distance depends on the concentration of this micelle.
Okay, thank you. I think we will now open for the we call open discussion. So if you have any questions, you can directly ask the speakers, or you can have a comments, or speakers can also ask questions and comments. So it's open for the discussion, and you can speak directly, or you can also write in the chat. So I think I will start with Professor Sanjog there about this interference phases, because what we also see in the photothermal, it's basically the same thing like interference. And we do see the ring pattern in the wide field imaging, and also this phase mismatch or the phase patterns which we see in the axial direction. And so one can read through this confocal scheme. But if it's in the wide field, then it's still, the problem is still there. So is there any way to get rid of it, or?
I'm not sure if I agree with almost everything you said. I don't know exactly what the question then would be. What bothers you in the, because you don't really have, do you have speckle problems in what you do?
Because if you have a wide field, then you do see this kind of ring patterns, right?
Right, but the ring patterns I mean, we actually like the ring patterns. In some of our other work, we take advantage of the rings to learn about the Z position.
Mm-hmm.
So one of the things that I didn't emphasize in my presentation, but we talk about in various papers, is that the traveling phase that gives you a contrast reversal leads to ambiguities if you want to track a particle over a large range, because after a few tens of nanometers, or let's say quarter of a wavelength or something, or half a wavelength, when the contrast has reversed, then if it reverses again, you don't know if it's now going up or down. But by looking at the rings, you actually can know whether you're going up or down, because typically there is a symmetry breaking because of spherical aberration that from your focus upwards and from your focus downwards, you don't have the same situation. And that tells us whether something's going up or down. So we actually take advantage of the rings. But so basically, if you have a single particle, then the rings can only be good. If you are in a very busy situation, then the rings of all the different particles would get into each other and give you a speckled thing that is a little non-trivial. And that's the thing that confocal gets rid of to some extent.
Yeah, clear.
Sandoda, it's great work. So actually, we're also very interested to see the possibility to incorporate your technique into these manipulation systems, so we may explore new opportunity. So how easy for implement this system into like a new Nikon system?
It's very simple. I mean, we also use the paper that we published was measured on a Nikon confocal. So you literally need to change one element where you have a dichroic mirror. You can put a beam splitter, then you get everything. Or maybe from model to model, it's a little different, but basically it's very compatible with an existing setup. You almost have to do nothing, because the usual excitation beam that is wasted in reflection, you just need to collect that.
Nice. Cool.
We would be happy to walk you through that. Just write an email and we'll.
Thank you.
Make sure that you get that working. Yeah.
Mm-hmm.
Please go ahead if anyone has any comments. Yeah.
I have a question to Professor Chen. So you showed this steering. So I think it was in 2D. And then you mentioned about this collective behavior of the that you study the collective behavior. What kind of effects do you see there? And could it be also extended in 3D? Are you able to steer in 3D?
Yes. So for study collective behavior is we try to understanding how a school of fish or flock of birds, how they work. So you can directly measure them when they do that, but it's hard, right? It's hard to measure fish in the ocean when they do this schooling. So we use an individual particle mimic each of these fish. By saying mimic is that we give each individual particle the capability to detect their position and also their capability to sense the neighboring particle position. So that's exactly what the fish is doing. Right? So they see that they are neighboring fish. So when they see that, at each moment, they try to align their velocity to their neighboring fish. So we're using the same algorithm to control our laser beam for this basic function. It turns out the collective motion, the pattern can be replicated. So we think maybe is a working principle.
So you're changing the rules of kind of steering, yeah? So how you put the laser,
yeah.
So you change this.
Yeah, we change their interaction rules. Try to mimic.
Yeah, very interesting.
Yeah.
And is it also working in 3D somehow?
Exactly. So 3D, what so far I introduced is based on we heat the substrate, right? So which is limited us to 2D situation. But for 3D, the particle itself has to be absorb light, so become a heating source. So if you have silicon particle can absorb visible light, we can create 3D manipulation. We have a few papers published on that that didn't talk today.
Yeah, thank you very much. Yeah, very, very nice.
You're welcome.
Thank you.
So if everyone is quiet, then maybe we ask questions that shows that I was daydreaming probably during the 1 or 2 slides that were completely critical in your presentation, Yuebing.
Yes, sure.
So could you walk me through again what exactly happens when you apply your laser field and how the trapping potential is established? I think I've gotten confused among the different applications, how that really works.
You mean this slide, this principle?
For example, yeah.
Yeah. So this is cross section, and this is substrate. So when we laser beam shining here, this part get heated up. So this region is hot. And
so can you say something? Sorry if I interrupt you, but could you say something about the substrate? What kind of substrate is that now?
Yeah, substrate can be any substrate can absorb this laser beam. So here we're using green laser. So, but here in order to enhance the efficiency, so we can using low power, and we're using plasmonic. It's a network of small golden nanoparticle.
I see. So okay. I see. So it's, but do you have to worry about, but you would assume that it's basically homogeneous, or do you go to one of the nanoparticles and?
It's a network. So it's a random. It's a random distribution. Yeah. So, but their particle size is much smaller. So maybe one laser beam location, you have several particles.
Okay.
And this random. The reason we want them separate is because we want to reduce the thermal conductivity, so that we have localized heating source. If we're using continuous thin film, it will dissipate. So our trapping will be not confined.
Yes, got it. Okay. And then?
So yeah, so once we have this temperature gradient, so since this cross section, and all the particle, we have this particle we are interested, is maybe a polystyrene beads or bacteria. Yeah. So this is micelle, this is ion. So thermophoresis tells us all the particle will move away from this hot region, right? But this micelle, but their speed is different. So it depends on
sorry, so that means that your particle needs to live in a suspension that includes micelles, micelles, that it if you just had a normal salt water or something, it wouldn't work.
It's also work that if like this, let's say you have salt. So in salt you have sodium positive, chloride negative. So in this case, the micelle will be replaced by sodium, which is positive charge.
Right.
Chloride is negative, so you still form this electric field.
But I understood that you rely on the fact that one of them is heavier and moves faster than the other one.
Yeah.
But in the case of sodium and chlorine, do you still count on one of them diffusing differently?
Yeah, still different. We have one paper actually studied this, compare even in DI water, it can still work because DI water you have a polarization, spontaneous polarization of a water molecule, can still create an electric field. So the reason here we're using surfactant is the first example experiments my former postdoc Professor Lin did. So he accidentally added this and coating the particle with charge. So that he found this phenomena, but later on actually it can extend into other systems.
Okay,
yeah.
Perfect. Thank you.
You're welcome.
And does your but your particle doesn't have to be charged. It can be neutral. It's thermophoretic, or
so in this phenomena, your particle has to be charged.
Oh, it has to be charged.
Yeah. So only you charge, then you can feel the electrical force.
I see. And was there a scheme where your particle didn't have to be charged?
If you're using a different phenomena, so it won't be charged. For example, if we're using pure thermophoresis, in this case, you don't need. In this case, we simply using thermophoresis, using the capability of a particle move from colder region to hotter region. In this case, we don't introduce some electric field, but simply thermophoresis. But we need cooling down the environment so they can flip the direction of motion.
Yeah. Okay. Thank you.
You're welcome.